Good afternoon. Welcome to the last day of classes this semester, huh? All right. As always, this is a pleasure to introduce our students who are going to present their senior capstone research today. We have 7 talks today, so I'm really going to hold them to that 5-minute limit, and the mic may be muted if need be. So with the 5-minute limit, then they can take a question while the next speaker gets set up, and then we'll move on. But as many of you know, here in physics and astronomy, we love having our students engaged in research, and in particular doing an intense senior capstone with one of the faculty on various topics. So today we have a wide range of physics, astronomy, and borderline engineering for some of them presentations on what research our students have done for their capstone presentations. And before we get started, I was told that I could not take the mic and not remind you that tomorrow is our annual Space Physics and Astronomy Forum. It is in Building 57A from 2 to roughly 3:30. I have been told that Dr. Huey is arranging for snacks, possibly donuts, and that they will be there then. And so please, please, please come and tell us what you think about different things within our curriculum so that we know how to make it better for you or for future use as that comes through the department. That's the only way that we as professors can really improve our curriculum, make sure that it's meeting your needs as well. So that is tomorrow, and there are snacks. Now, first up today is Amanda Holdsworth. Amanda has been working with me on a Wolf-Rayet binary. She'll hopefully tell you what that is, or you'll remember from Randy's talk a couple days ago. And in particular, she'll be talking about a 3-dimensional orbit for a system called WR138, even though she didn't put the full title up on the slide. So Amanda is not only finishing this year with her degree in space physics, Amanda will be staying in Prescott and teaching at Basis next year. She'll be teaching physics to middle schoolers, which is really, really fun. So congratulations to her. She has a job already lined up. And Amanda, without further ado, please take it away.
All right, hi everyone. I'm super excited to be here and share what I've been working on these past few years with Dr. Richardson, and I would like to give a special thanks to Space Grant for funding part of this project. Okay, so before we get into the meat of this, we have to cover a little bit of background. So Wolf-Rayet stars are believed to have evolved from massive OB-type stars, and they're classified by strong, broad emission lines rather than the normal absorption lines of typical stars. Wolf-Rayet 138 in particular is a nitrogen-rich Wolf-Rayet star, which is believed to be towards the end of the evolution of these types of stars, and it's in a binary system with an O-star companion. Our goal of this project is to resolve this system, which is basically determining the masses of the 2 individual stars along with all of the orbital parameters. And if we're successful in this, then this will be the second WN star to have ever been resolved. Oh, sorry. Okay. So in order to determine these parameters, we have to first extract all of the radial velocities from our spectra. So in the top left, you can see an unnormalized spectrum. And what I did was I did a polynomial fit to the background, which excludes all major peaks, just so I don't skew my fit value. And I took that fit value, divided the whole spectrum by it to normalize to 1. Now we can see this really bright or really strong emission line at 5411, which is a helium-2 line. That comes from the Wolf-Rayet star. So what I did was, instead of doing a normal Gaussian fit, because the top is too variable over time due to interactions and strong winds, I had to fit the sides of these peaks using a bisector fit, and if you're here for Randy's talk, you would know what that is. And from those, I averaged the center value, which I then converted to wavelengths, or converted the wavelengths to radial velocity into the plot on the right. For the O star, it's a similar thing. We can see around 58, 55-ish is this absorption line, which is from the O star, and this doesn't vary as much over time, and so we could do normal Gaussian fit, take the center, that center wavelength, convert it to radial velocity, and get our plot for that. We can also see two absorption lines right next to it, and those are interstellar sodium lines, which acts as a baseline for us. Because it's not from our system, it shouldn't shift around over time. And so if we're noticing that shifting, we know that our data needs to be corrected to account for that. We also took some interferometry data up at Chara at Mount Wilson, seen on the graph on the right. That star in the middle, that center 0, 0 mark, is the brighter star, which is the Wolf-Rayet star. And then the circles, the black circles around it, are the measurements taken for the O star, with the little red bits in the very center are the error ellipses. So we can see that our uncertainty is pretty good, given that our axes are in milli-arcseconds. So we took all of this data, all of these radial velocities and interferometry data, combined it into one big thing, and found some preliminary masses. And then we ran into some issues. So we got a preliminary mass of about 6 solar masses for the Wolf-Rayet star and 8 solar masses for the O star, which should cause some concern because O stars are typically in the 40 plus solar mass range. So we took another look at our radial velocity data, and I only have raw data for 3 of these data sets. All of the other ones came from literature. And what can happen when we're analyzing the literature data is the way that they reduce their data can cause different offsets. And so I went back in, looked at those offsets, and kind of adjusted accordingly to get all of them to overlay properly, which can be seen on the bottom graph. Comparing the two, it's a lot nicer to look at. So with this new data, we're going to rerun our code, get new preliminary masses, get new orbital parameters, and then from there, we'll send it to Jan Eldridge at the University of Auckland in New Zealand, and what she will do is she will determine the evolution of the system. So looking at mass transfer over time to determine kind of how these stars came to be, how they interacted, and potentially where they're going. We're also going to compare all of this to X-ray data from literature to confirm that what we are seeing matches with the X-ray results that they were getting. So very exciting things. I'm excited to finish this out to the end, and I would like to take any questions if there are any.
As a question, I thought I would. You need to go. Don't put the other one up yet because we have to. I have to ask a question about the slide, or leave it somewhere. There it is. Yeah. See the lower graph there looks much better, but it looks like it's going to have the same. There it is. Period, as the one above it. So aren't you going to get the same masses then, or what will change?
So what happened? So our two. It's kind of hard to see, but if you look at the green stars and the blue diamonds on the top graph, those two are our best data sets, and they're offset by each other. And so part of determining the masses is taking the amplitudes, and because they're offset by each other, it skews the amplitude value, which then skews the mass value.
Okay. Thanks for explaining.
One quick one. Quick one is just, what kind of uncertainty do you get on the mass values of the stars? Like, is it
like
fractional, like 1%, less than that?
So both of them were about 3 plus or minus 3 solar masses. Yeah, it'll be a lot better once we have not unbiased, but unshifted data.
Okay, thanks.
All right, Dr. Pradhan is going to introduce our next 2 speakers.
Okay, so I'm here to introduce Tristan and Sam right here. For those of you who don't know, this is Tristan right here, and Sam is sitting right here next to me. I'll still remember the first time Tristan and Sam came to me when was it? Fall of 2020, and they were like, can we work on you on a research project? And I was like, sure. And then they've done so much work since then. Because I have a mic, I took this opportunity to kind of embarrass them. But this is the most embarrassing photos I have them, so nearly not that embarrassing. But this is them presenting at the Arizona Space Symposium. They really did a great job of doing that. And then we next have them recently. They've evolved a long way. This is them presenting their, oops, can I not say, hold on, so there you go. Oh, so there you go. I think so. See, he's helping me embarrass him, but there you go. Yeah. So anyway, let me introduce Tristan in a while. Tristan is currently working with me on a very rare system, symbiotic extra binary GX1+4, and you'll see the amount of work that he's done putting into it. Tristan has been obviously an exceptional student, as you all know. He's also been, for those of you who don't know, he's also been awarded an outstanding graduate this year. So, that's really cool. He's among the top 5% of the senior graduating class. And for, at the end of his, once he graduates, he'll be joining Penn State University for, he's joining actually the best group in higher energy astrophysics that there can be in the world, obviously in the US, but also in the world. So yeah, I very much, I think it's well deserved. Okay, and this is them. They've come a long way. This is the photo that we had yesterday, and they are there. The ones at the top, but they're putting their ducks in a row. But here you go, Tristan, take it away.
All right, hello. Let me get back to mine. And there we go. And present. All right, can everybody hear me all right? Perfect, all right. So, as you were just saying, I was working on X-ray binary, exploring the variability of the symbiotic X-ray binary GX1+4 using NICER, Chandra, and NuSTAR. Those are all X-ray satellites. A lot of stuff to go over, so let's get into it. So, GX1+4, like I said, is an X-ray binary system. What is an X-ray binary system? It's a system consisting of some star and some compact object in a binary system. Star, who cares about it? But the compact object, it can be either a black hole, a neutron star, some enormous star that, when under supernova, became that compact object. But our system we have is so rare because we have this tiny little M star, which had to have just been that perfect distance away and perfect mass for our system to become the system that it is when that pulsar went under, or when the star went under supernova and became the pulsar. We also have a very horribly constrained orbital period from literature, no magnetic field value to date, and we will see that this source is very variable. So let's get into it. First thing we did was go over some different models we can use with our NICER data. I don't have enough time to go into all of this, but we saw that our best model was this fifth one down here, using a partial cover fraction absorption to deal with all of the stellar wind coming from the M star into the pulsar, as well as a thermal component, our black body, outside of the absorption to indicate some thermal source farther away. Feel free to ask me about this after. So for all about 30 NICER spectra we had, we plotted the spectral evolution over a couple hundred days, and if you'll look, you'll see that the bottom, the light curve, do not at all correspond with the increases and decreases in absorption, the NH you'll see in orange and purple. There is absolutely, or very little correlation, which really shocked us. And if we look at the plot on your right, you'll see that there's pretty much a linear trend between the iron line we've been analyzing and the continuum flux. And you'll see that we have quite a few outliers that have made this whole thing quite a situation. So as the continuum increases, our iron line we're detecting should be increasing, but at some points we see this crazy difference. And talking about that crazy difference, here are a couple of these outliers of NICER spectrum that I've generated. And we'll see that from these four, some of them don't even have an iron line, some of them have enormous iron lines and tiny continuums, and some of them have really tiny iron lines. These are all of those variations in that plot that we just saw. So we really have no clue what's going on looking at that. So we move on to Chandra. Unfortunately, Chandra wasn't able to show us much more than that. Fitting our 6 Chandra we had, we were able to see, though, a comparison between 2005 and 2022, the broadening of the iron line that we've been looking at, that we were plotting as a function of continuum over about 15 or so years how much that line has broadened, and we'll see why. This is actually taken during an extended flaring state of the source. We'll get into that. So after Chandra and NICER, we did all that analysis, and then we presented this, and they had the idea to go to NuSTAR, a third X-ray satellite. But unfortunately, there are no really good NuSTAR observations of this source, so they talked about stray cats. So NuSTAR has a huge field of view. And so that right there, that's not my source. We actually analyzed the red, the very colorful. That is not my source. The blue on the side, that is my extremely out of focus source that we were able to get just a few photons from to get that spectrum on the right, which is very awful. We weren't really able to get very many photons and see anything that we really wanted to see in the higher energy values, but it was good to see that NuSTAR Stray Cats actually works. We're able to get some information from it. And so from using that, we actually put in a NuSTAR proposal that I'll talk about in just a little bit, going into some timing analysis. Since the discovery of the source, we were able to use Fermi data to show that the spin has actually doubled. The spin period has doubled since discovery. And if we see here on the bottom, the Chandra data was in red and the NICER data was in purple. Our extended low state for NICER, extend our flaring state for the Chandra taken over there, to see just how much of a flaring state that was in. And some more timing analysis. What we wanted to do with our NICER was make some nice pulse profiles like they were able to make with RxTE back in the day. But unfortunately, NICER and Chandra are not, the observations were too short, Chandra's not the best, and we weren't able to really get a good pulse profile. So, moving on from that, we submitted a NuSTAR proposal that we did get, where we will be analyzing the source for the next 9 months to really get good values for our, I'm getting the eyes from Dr. Richardson over there. Anyway, so the final conclusion is what is causing all of this crazy variation? Because we're seeing nothing's making sense. A couple of things. Should look at this. The onset of a propeller regime, which in the system the accretion is preventing the absorption. The clumps in the stellar wind further away, preventing us from seeing the absorption, as well as something called quasi-spherical accretion, which I've unfortunately ran out of time to tell you about. So please ask afterwards if you are curious. But we are waiting on that NuSTAR proposal to get some more information.
So you said the pulsar doubled in its spin the last time you took the data. What do you guys think what caused that? I mean, from my assumption, I'm thinking the radius would have had a decrease for the pulsar, so the angular momentum would be conserved, but what's your idea on that?
This, this is an accretion-powered pulsar. So it's a pulsar with an M-star. All of the accretion coming in from that M-star is slowing it down. Usually we know pulsars to have like millisecond periods, really, really fast. This one's in the hundreds of seconds. It's in the minutes. Yes.
I see. Thank you.
Any other questions? So since I have the mic, I can go ahead and introduce Sam right here. Sam was working with me the same day as Tristan started, which was, fall of 2022. And for those of you who know Sam, he's like the coolest, most calm person I have ever seen. So, you will see him like talk about a really exotic Loma 60 binary 41822-371. Now, I should mention here that Tristan and Sam were the first students who actually set up the Linux machines at the R2 lab. So if you're using that, you have to thank them. Sam is currently, on the job market, looking for opportunities to, mostly involved with scripting and involving a little bit of astrophysics. And I'm sure any institute will be very lucky to have him. So take away, Sam.
So everybody can hear me, right? Okay, cool. So I'm Calvin, but also Sam. You can call me whatever you want. At this point, I might just go by Sam because I think it's cooler. So yeah, I'm gonna talk about my source today. It's 4U 1822 371, which is an ADC source. So real quick, I'm just gonna talk about my source. So it's just a low mass X-ray binary, pretty much the same as Tristan's. We have a compact object and a low mass star. We really don't care about that star, but we really care about that compact object. So in the case of my system, we have a neutron star. And these are also older compared to high mass X-ray binaries. The main thing about my system is that it has an accretion-dominated corona. What is that? So we have this little picture right here. So we have our companion star, which is the one that we see, the big giant circle. And we have my neutron star, which is hidden in the middle. We have the accretion disk, which is covering the neutron star. And we also have a corona that's around that star. And so what we usually see is a lot of scattering from the corona as well as scattering from the accretion disk. And also my system is at a near 90-degree angle. So when we're looking at it kind of like this from the side instead of head on, like on the top. But why do we want to do this one? So in literature, we've seen evidence of cyclotron lines, which can help us directly measure the magnetic field. It also has a very high magnetic field for its age. Since low mass X-ray binaries are older, we usually should see a decay in its magnetic field, but we haven't really seen that. So in literature, we've seen about 10 to the 10 or 10 to the 12 Gauss for its magnetic field. And just for a comparison, the Earth's magnetic field is just a half Gauss. There's also only been a couple of low mass X-ray binaries that have a cyclotron line, so this one was really worth looking into. So the first thing that we were looking at was our emissions coming from inverse Compton scattering. So what is that? So if we look at this picture over on the side, we see that we have matter from the companion star falling into the neutron star. And as it's falling in, it emits these X-rays that we can then see. And there's also been like debates on the existence of the cyclotron line. And so there's currently two competing claims, which was the two different magnetic fields that we saw around 10 to the 10 or 10 to the 12th Gauss. And then we also were thinking, well, where else could this emission come from? So we have our other idea, which was reflection. So we have reflection from the accretion disk. So when we have the X-rays coming out of the neutron star, they get reflected off of the corona and off of the accretion disk. And so when we look at it through our, when we look at the spectrum, we should see a characteristic Compton hump, which is around like 10 to 30 keV. And this is just due to Compton scattering. And we first looked at NuStar. So NuStar was our cute little satellite right there. This is just a hardness ratio. They have really long observations. We have about 10 to the 5th seconds. So, oh my God. I know. I should go faster. I'm just going to skip this for now. We basically, these are good for detecting cyclotron lines. And so we did 2 different models. We did just a regular power law model, and then we did a reflection model. So we see that our reflection model is a lot better of a fit than just a regular power law, which is kind of giving us like an idea of what's going on in the system. And so we were like, okay, well, let's go look at NICER. NICER, we basically did the same idea here. We just did power law, and then we did also reflection. And so far, I think reflection's really cute, and I think it's like the best one. So in order to figure this out, polarization is the best way to figure out, like, definitely figure out which one it is. So we have a higher polarization of reflection, and it'll show a clear difference between the two. In the future, we really want to get an IXP proposal. We did submit one, but we were barely just at the cutoff. We were like the next one in line, and they were like, no, sorry. So we're going to hopefully get a proposal in. We're going to look more into reflection because I think this is what's happening in our system. And I also want to work more on the nicer analysis because I didn't spend a lot of time as I did with NewStar. So that's it. Thank you so much. And I hope somebody has a question for me. Don't be mean, though. So it's basically just like when we have like a magnetic field and we have like a particle. Basically, it's kind of like, imagine like you throw a particle into like a washing machine, and then that washing machine kind of just emits like a bunch of like emissions. That's just kind of what a cyclotron line is. But we can see that. We kind of see like a little like a dip towards like the higher end of the spectrum. So that's kind of what the line, the quote unquote line is.
All right, let's thank Calvin again.
While Zach's putting his talk up, I'd like to give a context for what he's doing. In past years, some of you don't know this, but we have a cosmic ray detector in STEM next to the optics lab. And looking at cosmic ray muons, looking at them stopping, not a small fraction of them stop in the detector, but when they do, they decay. And Zach is going to talk about these decay particles. We've measured the lifetimes of these decay particles, and we've done this all in the past, but what he's going to do is something a little bit different, and that is to look at the energy and the energy distribution of the what's called the Michel electrons that decay from the cosmic ray muons. So, Zach, go ahead and take it away.
Thank you, Dr. Smith. Hello, everyone. I'm Zach Herzog, and like Dr. Smith mentioned, I'll be going over measuring the Michel electron energy spectrum. So, to start off, what are cosmic ray muons and Michel electrons? Well, cosmic ray muons are emitted from the sun, and as they travel here, they lose kinetic energy and eventually decay. And we're looking for decaying muons as they enter our detector. And our detector is inside this barrel is a 5-gallon bucket filled with liquid scintillator and mineral oil, and on top of the bucket are 3 photomultiplier tubes, or PMTs. And so as the cosmic ray muons decay in the bucket, they interact with the liquid scintillator and release light that then gets detected by the PMTs. And sometimes when the muons decay, they will also emit an electron, which is the Michel electron we're looking for. And we're able to find pulses like shown there, where the Michel electron usually is emitted roughly 12 microseconds after the muon decays. And we're interested in finding the area under that curve because it directly corresponds to the energy of that electron. And so we're able to see pulses like these from the picoscope that we use, as shown here, where we take the raw pulses of the raw pulses from the PMTs that go straight to the picoscope, and as the pulses are in coincidence with each other, we're able to tell that that is a Michel electron, since when there are other pulses without any other pulses from the other PMTs, we can tell that it's just noise and not what we're looking for. Another thing we can tell from this is that the size of the pulses is different from each PMT, and so we want to be able to make them comparable to each other, so we make them comparable to each other, and we do this by determining the operating voltage. And so I basically took the average counts of each of each PMT at different voltages and saw what their outputs were. And I landed with finding with them with 100 counts per 10 seconds is where they have like where they have similar outputs. And so I took the corresponding voltages at each PMTs. And the reason why I did this was because each photomultiplier tube reacts differently at different voltages and is able to take in light at different ways. So this is why we did that, to make them similar to each other. So now that they're similar to each other, we put them through this logic system where we have all the PMTs going through an amplifier that keeps in an analog format, and then they go into an LTD that makes them digital, and then we put them into a coincidence unit, so they only show up when both PMTs see something. And then they go into the picoscope, where we also have a raw pulse from PMT2 that preserves the raw pulse, so we can find the area under that curve. And so most of the data I collected was triggered from the picoscope that only triggered on the second pulse of the when there's a second pulse from the coincidence between PMT 2 and 3. So, as shown here, here are some examples of these pulses we found, where the image on the top left is one where all three PMTs agree that they saw a Michel electron. And so the graph under it is the area we found for that pulse. And then the same thing with the second image on the top right, where only one of the coincidence pulses agree that it saw an electron, but we still take those. And so we measured the area under that pulse, and we're able to create some histograms using these data, as shown here, where I only took 44 pieces of data, but the first histogram basically shows the distances between the muons and the electrons, where the second histogram shows the shows the Michel electron energies, where we have a few outliers, and the last graph is basically the theoretical distribution that we expect to see of the energies of the electrons. And so, yeah, that's pretty much it. And for the future work, we want to take more data, use cosmic ray detectors to know that we actually see a cosmic ray, and then and to collect better data by automating the data collection process, as well as investigating those outliers, and to improve on calculating the area. Thank you. Are there any questions?
Are there any questions for Zach? Really, guys? Come on. All right, we got something over there.
What do you think is causing there were maybe like 5 or 6 outliers on the far right part of that graph. You don't need to go back into it, but yeah, the outliers on the middle plot, what do you think is causing those?
I think those outliers are due to just like issues with issues with the equipment of I think it might also be due to where the muons decay, how they could decay in the actual PMT and not like when the light emits. It makes it a lot stronger, and so it can impact the area of those pulses.
Let's thank Zach again.
Good afternoon, everyone. I'm Dr. Quentin Bailey, if you don't know me. Alex has been working with me for several years on a theoretical research project, so this talk is going to be different from the other ones in that it's theory. So I try to come up with projects that are accessible to undergraduates in theory. And Alex, this is actually the second project Alex has worked on with me. He was involved with another project on understanding fields in space-time with Lorentz violation, and he's gotten quite crafty with Mathematica, which maybe some of you have heard of. So you'll see some plots from that, and he's doing theoretical calculations. We decided to study trajectories in space-time for accelerating observers, which is not even something you learn in modern physics, so that might be interesting. But then we're looking at what happens when you have Lorentz violation as well. So this will be quite a different talk. So, and then after Alex is graduating, obviously, and then he's looking into industry or graduate school. So take it away.
All right, thank you. So like Dr. Bailey said, I'm working on space-time trajectories of accelerating particles with Lorentz violation. A little bit of background. The problem that we're basically trying to solve is the fact that currently relativity and quantum mechanics are incompatible with each other. So Einstein, when he published his famous paper in 1905, outlined a lot of the principles of special relativity. Some of those being the fact that relativistic objects undergo length contraction, and clocks at those relativistic speeds actually run slower than those that are stationary. And one of the consequences of this paper are the principles of Lorentz invariance and Lorentz transformations. So Lorentz invariance basically states that experimental outcomes will be the same when your apparatus undergoes Lorentz transformations, which are known as rotations and boosts, boosts being accelerations due to some force. And the research that we're doing is we want to look at what happens when this invariance is broken. So if you do your experiment under a rotation or a boost, the results you get would actually be different. And you can describe this violation with background fields in space-time. So the specific example that we're going to be looking at is examining the trajectory of an accelerating particle under the influence of these fields. So when you're analyzing gravitation, it's helpful to represent gravity as an acceleration, which we denote with little g there. And with these three equations relating your force velocity to your force acceleration, you can derive equations for the time and position of your particle with respect to proper time. So you get hyperbolic sine for time and cosine for position, and then plotting them parametrically gives you this hyperbola that shows the trajectory of your particle. And as you can see, the force velocity and the force acceleration are orthogonal to each other there. So to model the background field of Lorentz violation, we added an extra k term to our standard equations and get these modified equations you see at the top. And then solving them, or attempting to solve them, we can get these third order differential equations of time and space. And then those with two different sets of initial conditions give us these modified hyperbolas. So you can see the solid line is our modified trajectory curve and the dashed line is our standard curve. And so these are for the k00 case, where we isolate the k00 term and set all of the other k terms to 0. And then here we've got the k11 term, where in the same way we look at k11, set all the other k terms to 0. And so we've got our different third order differentials right there. And then solving them with our initial conditions gives us another modified curve. And the interesting thing about the K11 case that we looked at is that assuming one of your initial conditions for force velocity actually implies the second case that we looked at. And so instead of having two sets of initial conditions and two plots, we only get one plot. And one interesting phenomena that we had in the K00 case is that with the third order differential equations, one of the sets of initial conditions led to a breakdown in those equations. after a certain distance away from the origin. And so that's why in this graph you can see that the modified curve is slightly cut off from the standard curve. Thank you. Any questions?
So your presentation was about like if something breaks at, what was your presentation again?
No,
Like-
that's fair. That's fair. It's broken Lorentz symmetry. So we're looking at what happens when. So currently, under the physics that we understand, experiments, when they're subjected to a rotation or an acceleration, the physics remains the same. And so we wanted to look at what happens if that doesn't happen. If when you rotate or boost your experiment, you would get different results. And so we did that by analyzing the trajectory of an accelerating particle in space-time.
So it has to follow the Lorentz, or is like it's still classical in that sense, or?
Not classical. One of the consequences of Einstein's research into special relativity was these properties that your experiments will stay the same under Lorentz transformations.
Zoe, get your thing open.
So why don't you use like the curvature of space-time instead of using the acceleration? Because the curvature causes the acceleration. It's going to be different for any mass in a field, right?
I imagine it's much harder to analyze that kind of stuff. This was basically just the problem that Dr. Bailey set me up with.
Copy that.
All right, let's thank Alex again.
Thank you.
We have two more talks today, the first of which is Zoe Spangler. Now, I met Zoe when she enrolled in my Physics 3 for Engineers class, but she realized that she wanted to be a physicist more than an engineer and switched her major over. She spent a bit of time the last couple of years working with Dr. Zanelin on LIGO stuff, but Dr. Zanelin was on sabbatical this year, so she came back down to my office and said, hey, can we do something together this year? And so we came up with a quick project for her to try to get through this during her senior year. She's been doing some great work, working on understanding how some stars called BE stars vary with time. Zoe is looking for a job after she graduates next week. So if you have any leads, let her know. And other than that, thank you very much, Zoe. Take it away.
Thank you. Okay. Thank you, Dr. Richardson. All right, so my name is Zoe Spangler. It's nice to be here and talk to you about BE stars in the Pleiades today. What even are BE stars? They're rapidly rotating B-type stars that show Balmer series emission lines. So because they're rotating so rapidly, mass ejects from the star, which creates a circumstellar disk. And we can see that. So I looked at M45, the Pleiades. It's an open cluster in Taurus. If you haven't seen it, it's to the right a bit of Orion and just kind of like a little fuzzy patch. But if you look closely, you can see 6 or 7 stars with the naked eye. 4 of them are BE stars. That's Pleione, Merope, Alcine, and Electra. Oh, and you can actually read them really well up there. That's nice. And one interesting thing I found was that in the northern hemisphere, like in ancient times, the rise of the Pleiades would signal the beginning of seafaring and farming seasons. So here I made it a little bit more clear, like which 4 you could see that we're focusing on. And in this, if you look closely, you can see that they're special because there's that little bit at the top. It dips. And that's what makes it the BE star. how do we get our data? We use TESS. We got light curves, which TESS takes a data point every 20 seconds to 30 minutes, depending what the goal is when observing a star. We got about 5 months of data on the Pleiades on 4 different stars. I focused more on Pleione because that's where I saw something kind of neat. And I used Period 04 to analyze this data, which was something new to me. And it made it really easy to do Fourier transforms, which, if you've experienced, aren't that fun otherwise. So I was really grateful for Period 04. A little bit on Pleione, early days in 1938, we found changes in spectrum attributed to a gaseous cell that dissipated by 1952. And then we got a little bit more data in the 90s of a period of 218 days and a large eccentricity of 0.6. And then we saw that it transitioned from a BE phase to a BE shell phase in a paper published in 2022. And then this year, I've been studying it, so I put myself up there too. And now for the fun part, the data. We can see disk activity. So I highlighted it so you can see up there. This is the whole light curve at the top graph. And then the bottom graph is just kind of that section that I highlighted. And you can see that there's that rise and fall in the data. And that is, so the high amplitudes in the light curve, it can lead to the disk building. And then once they start destructively interfering, the disk starts to settle down, which we can see basically exactly happening. What we think is happening. I wasn't there personally. And then a little bit more, the top plot is my Fourier data from Period 04. And then the bottom is the residuals, so you can see that disk activity in that as well, where it's almost the same. And then to compare, because that kind of just looks like lines, you know what I mean? These were the other stars, so especially in the residuals, you can see there isn't much change overall. Not like we saw with Pleione, where it had that weird part at the beginning that we also see in the residuals. And that's it, yeah. Any questions?
All right, looks like we have one question.
No way. Could you go to the slide with the purple data, or sorry, the purple fit and the blue data? I think I might have missed it, but what fit were you doing?
This one?
Yes.
So I did a Fourier transformation. So basically, that blue is the raw data. Oh, maybe I should have said that. So the blue is the raw data. The purple is my fit. And you can see it doesn't follow it when it goes up and down with that disk activity, which I think could be another sign of it. But it's a Fourier analysis, so different frequencies. I can't remember exactly. Kind of like about a dozen, yeah, plus or minus couple. And then it's summing sinusoids.
Okay.
Yeah.
Got it. Thank you.
Can you go back? I think it's one slide. One more. Where's the one that had the frequency at the top of the plot?
That one.
Oh, yeah. So that frequency has, 12 digits? What's up with that, with the significant figures?
So,
Come on.
that's fair enough. That is a copied and paste. That's copied and pasted from Period 04 because I wanted to be as accurate as I could be.
It's slight overkill, but she has it to like 7 or 8 decimals, so we'll give her that. Let's give her another round of applause while we're at it, too.
Thank you.
All right. While our last speaker sets up, one more reminder, Physics Forum tomorrow. Come get donuts. Also, after the talks for all of our graduating seniors, including the ones that gave a talk on Tuesday, do not run away. We want a picture of all of you in here for the department, okay? So with that in mind, I'll let Dr. Smith introduce our last speaker.
Thank you, Noel. Our next speaker is Alvaro Flores, and Alvaro's been working with me for the last couple of years, starting with nuclear thermal propulsion, something you heard about 2 days ago from Dominic Darlington. And Alvaro wanted to do something slightly different, and that is to look at what I call medical physics, because the question is, when you do a round trip to Mars, the question is, the cosmic rays are going to impinge on the spacecraft and on the human beings inside the spacecraft. The question is, what's it going to do to you? And so he's investigating the biological doses that people will get in a manned mission to Mars. So he's going to talk about cosmic rays and human spaceflight, the biological impact. Take it away, Alvaro.
Does this one work? Yeah, it works, right? Yeah. So yeah, I'm Alvaro Flores. This is my presentation on my thesis, just the biological impacts on cosmic rays during a manned mission to, for this instance, it's Mars, but could also be applied to anywhere. So right now, my main research objective was just to evaluate the effectiveness of passive shielding methods. The reason I say passive is because my engineering professors have recently told me that there are active shielding methods that can be more effective. So I felt like I had to specify that this is all just passive shielding methods. The specific goals that I had in mind for this was to just test different shielding methods, as in different materials, different thicknesses, to see what absorbs most of the high energy cosmic rays that one would encounter in such environments. Apart from that, just relate those cosmic rays into measuring the radiation damage that a person would receive, and then assess the biological damage by looking at NASA standards, IEEE standards, and other sources to see what exactly can happen when you absorb such amount of dose. So my methodology for this thesis was to first compare 3 different programs that I was planning on using, and that was MATLAB, OpenMC, and as well as JAUNT4. I ended up choosing JAUNT4 because, as Dr. Smith just said, this is a medical physics problem. JAUNT4 is already designed to handle these type of problems in the medical physics field, and so being able to adjust that for my research was very easy and straightforward. The only big issues were trying to learn it. You're not just learning another program, but also a programming language, and the source and documentation for this isn't really straightforward onto how to set things up. But this is how I ended up setting it up. So on the left, I just have a very simple spacecraft, just a cylinder with 2 caps, 1 on each end. It's all made of aluminum, just very simple model, and it's about 20 centimeters thick all around, which is very thick. And in the middle, you can kind of see like a blue cylinder that's a lot smaller. That is just a small volume that models the average human size. So it's 1.6 meters in length and about half a meter in width and diameter. And so this is about what the average human is in size and volume. And on the right side, it's an image of what would happen when I would run the simulation, and we get all kinds of craziness going on. And all of these lines are different colors because they represent different particles, such as your protons, alpha particles, electrons, gamma rays, and the list goes on and on and on. So once I ran that simulation on the right, what I did was I took the sensitive detector volume, which was the blue cylinder from the previous slide, and I did a bunch of volume cuts to be able to more accurately determine the statistics and the energies deposited into very specific regions of the volume, more as to like trying to see if a person got hit more in the leg or in the arm. That's what I looked at. And looking at this one on the left, most of the energy gets deposited in the middle, which would kind of be like your torso, your stomach, close to your liver. And they're somewhat high energy, and the highest that gets deposited is about 2.5, close to 3 giga electron volts. And on the right, what I did was just plot the volume number. I had 160 different volume cuts that I did, and then just plot the highest or the average energy in each one, and took an average, which resulted at about 0.275 GeV per volume. From here, I did a lot of more analysis and coding and diving deeper into the results that I got and the data that I collected from the simulations. And from the number of particles that I simulated as primary particles, I was able to get that the actual real time simulated for a trip in space is just 2.1 milliseconds, which is such a small amount of time in space. And the amount of radiation damage that a person accumulated in that small time is 48.5 femtosieverts, which is like 10 to the minus 15. And then from there, I just got a sieverts per second rate, multiply that by 540 days, and then was able to get that a person in a Earth to Mars and then back to Earth transfer would accumulate 1.062 millisieverts in total radiation damage. Right now, the NASA limits for a career for the astronauts is 400 millisieverts for men and 300 millisieverts for women. So far with this overkill of a shielding, we're well below those limits. And for my next steps, it would just be to take this further and test out different methods and also try to see if I can minimize the weight of the shield. Any questions?
Just is the spacecraft, the aluminum thing, was that the shielding method, or is that just like the in space what they'd be sitting in?
It was both the spacecraft and the shielding method. I kept it simple because trying to design a complex thing in Geant 4 would take ages, and that even on its own would be a thesis or a capstone.
So basically, you're saying that the aluminum itself is what was blocking all of the.
Yeah.
Okay.
So since the technology going to be used to get to Mars is going to have nuclear rockets, did you analyze like the source of radiation coming off an NTP engine at all?
No, I didn't take into account NTP engines because those are still theoretical and will probably still take about 40 years to develop. And a lot of current planned missions are trying to use traditional and current propulsion methods.
2027 we're launching Draco, so it's not theoretical anymore.
Draco's meant for a robot, not for humans. So
that's a mechanical robot, not a fleshy one. All right, let's thank all of our speakers again. Congratulations to our seniors. Again, if I could get all of our seniors that were presenters to come up front for a picture, we would really appreciate that. And I hope you guys have a great rest of your day. Good luck on your finals. And I look forward to seeing you tomorrow at the Space Physics and Astronomy Forum at 2 o'clock. Yeah, what? No, go ahead. What day is that? Next Friday? Tomorrow. Also, college awards ceremony. Week from tomorrow on Friday. Wear your caps and gowns. It'll be fun.